I'm so glad you made it out here. I expected like half the room actually to be gone already because I'm sure you guys are all exhausted. And there's also an ex-hurricane, which I'm pretty familiar with because I'm actually from Florida. So I was like, oh, they follow me wherever I go. Today I'm going to be talking to you about applicable and achievable formal verification. I work at a consultancy called Adelard. We're based in London, actually. And I do quite a few things. One of the more important things that I do that I'll be talking about today is that I evaluate, design, and specify, also verify safety critical systems. I carry out safety and security audits and assessments on client systems as well. And I help produce standards and guidelines for safety and security-related applications and their development. In a previous life, I was an academic. I have a computer science PhD from the University College London. I received them back in 2017, and I worked on temporal logic, model checking, verification of software systems. As a PhD student, I collaborated a lot with Microsoft research to build a model checker called T2 to verify temporal logic properties and a lot of different types of sort of systems we had at Microsoft, including Windows, especially device drivers written in C. So given that this talk is about formal verification, I realize that a lot of people actually have a lot of confusion about what it means. So I wanted to give a definition first and an example of what that looked like. So definition is the process of establishing whether a system satisfies some requirements or properties using formal methods of mathematics. That's usually what people are referring to. And the process of that looks a little bit like this. You first take some sort of system that you have, written in C, C++, or Java, and you sort of formally model it in some sort of mathematical framework that exists out there. The second thing that you're meant to do, or in parallel, is that you take your requirements and you write them in some sort of formal specification framework. You then take this model and this set of specifications and you sort of model check them against each other. You can use other techniques that aren't model checking, things like abstract interpretation, if you're sort of familiar with techniques, would work as well. But the idea of model checking is to exhaustively explore a system's mathematical model against a specification. So you're meant to sort of reason about the entire state space. And finally, if not all sort of specifications were satisfied, you sort of analyze their findings and you look at the consequences. What does that mean for your system? So this is sort of what I'm talking about when I mean formal verification. And what's a formal verification talk without this Dijkstra quote? It says, program testing can be used to show the presence of bugs, but never to show their absence. And this sums up why verification is important to a lot of people, especially in safety critical systems, because unlike testing, it can provide a proof or a guarantee that your program behaves as it's meant to. And this is what usually people think of when formal verification is mentioned. This is a theorem prover, and although a very valid technique, it's actually hardly used in the real world. It requires advanced expertise in formal methods and computational theory. It's also really resource intensive, so you need to be writing things like lemmas and theorems, and there's QEDs all over the place, and it can be like thousands of pages. And it's actually not very applicable in sort of the domains that I work in. So what accessible formal verification tools and techniques are out there? And that's what I want to be talking to you about today. I'm going to be first covering some standards guidelines and processes used for safety critical verification assurance. I'm going to be talking about an approach to the verification of a common type of a component in the nuclear industry. It's called the smart devices. Probably we don't have the same terminology here, but I'll talk a little bit more about that in a bit. Nancy gave a great introduction to the systems assurance side, but what I'll be doing instead is diving into a bit more detail about the assurance on a component level. And finally, I want to help you understand the range of formal verification tools available to use that are out there. So as I mentioned, a key role of my job is to formally verify safety critical systems. I know Nancy gave a definition of what a safety critical system is, but we all have slightly different ones. It's a system whose failure or malfunction may result in death or serious injury to people, loss or severe damage to equipment, property, and or environmental harm. And at Adelard, we work on many different types of systems. We work on aviation, automotive, and rail. Nuclear energy tends to be our largest sector, but more recently, sort of autonomous systems have been coming up behind that. And the industry doesn't use formal verification because it gives us a nice, fuzzy feeling inside. I mean, for me, it does, but I'm pretty sure regulators hate that kind of stuff and don't want to really think about it too much. But actually, we use it so much because standards oblige us to do so for a lot of different reasons, which I can't get into. But I want to talk about this Golden Boy standard, which we call IEC 61508. This is sort of the one standard that all safety critical systems have to abide by internationally. And up here is a table from the standard showing various verification techniques required by most safety integrity levels for the verification of a system. And what do I mean by safety integrity level? Well, you have hundreds or sometimes thousands of components in any sort of system that you're building, and not all of these components are critical as each other. Some of them are not critical at all. Some of them, any sort of failure can take the system down as a whole. So the way that we categorize how critical each component is through something that we call safety integrity level. And this is how they work a little bit. Well, I have two columns here because it depends. Your safety integrity level depends on the system that you have. You have systems that are based on the probability of failure per demand. And this is sort of the type of system that you're sort of asking a question of, like a temperature transmitter, for example, right? And then there's other types of systems, like continuous systems, and sort of their safety integrity level is incredibly more strict. SIL 4 is the highest level of integrity that you have from the standard. SIL 1 is the lowest integrity level. And to basically sum up what these integrity levels mean, for SIL 4, for example, you can only have one failure per 100,000 demands to, sorry, there's an extra zero there, it's 100,000, to 10,000. SIL 3, you only have one failure per 10,000 demands to 1,000 demands. And if you look at all the way to SIL 1, you only have one failure for 100 to 10 demands. So that's not very critical, right? You don't need to do much here. So there are different honors levels of formal verification and the diligence required for each SIL. So if you look at the table again, if you look at SIL 4, there's a lot of HRs there. What HR stands for is highly recommended, or really, in our speaking, it means it's required. That's what the regulator expects to see. R stands for recommended, and recommended really means depends on the situation. You might need it, you might not. And for SIL 4, we have to carry out a lot more of these techniques than for SIL 1, where mostly everything is sort of an R. There's more tables in 61508 that tell you the exact techniques that they want to see. But the thing about these tables in general is that it's a checklist approach. It doesn't tell you how or when or for what system you should be using these techniques, right? And what if there's alternatives? Should I be using one or all or together? And verification techniques are not a one-size-fits-all. Some of them are built for very specific systems. Some of them are built sort of for specific type of language, and so on. We could be talking about aviation, for example, where avionic systems can be built in-house and verified as a whole. The formal specifications of every component and functionality are written and verified together, and hopefully you use a technique like STAMP and STPA to think about what your requirements are ahead of time. And sometimes there are standards that might help with that. Each industry then follows its own substandard that branches out from 61508 and can provide a little bit more guidance on verification. So for nuclear, we use 61513. For automotive, we use 26262. And for aviation, we use 331. And this is considered sort of one of the more stricter standards because it requires end-to-end system verification of the emergent behavior of all the components together. But at the end of the day, end-to-end verification seems really overkill for the tech system most people deal with. But I was talking to someone the other day, and they told me that SRE people are always referring to sort of aviation as sort of the standard to measure themselves up against. But there's a different case that you may not be aware of that might actually resonate with the type of system that most people work with, and that's actually verifying nuclear power plants. This is a pressurized water reactor. It's not the one in Chernobyl, so don't worry about that. You're not going to die. This is the most common type of nuclear power plant that exists around the world, especially in the UK where I work. And the idea here is that you have two water systems. Over here, in the sort of the one outlined in orange is where your nuclear reaction is happening. This is sort of where the control rods are going up and down to heat up the water to incredibly high temperatures. You have a pressurizer to make sure that water doesn't boil or evaporate, because water sort of evaporates or boils under different temperatures, giving different pressures. The whole point of that system is to heat up another water system. And for that water system, the whole purpose is to generate steam, which can then power a turbine and then onto a generator. And this is how all of us get electricity. Now, each part of these systems, this is not one whole system sort of implementing the same technology. Each part of the system has what's called in it a smart device. There's a smart device looking at the control rods. There's a smart device checking the pressure. There's a smart device looking at the temperature or measuring the stream that's being generated. And they look a little bit like this. They're usually like really tiny, like this size, sometimes a little bit bigger, but they're not computers, massive computers or anything of that sort. And they're usually industrial embedded devices that are bought commercial off the shelf. They're not built in-house because it's not profitable to do so for the nuclear industry. So they just go to someone and say, hey, can we just buy this as is? And the manufacturer goes, great. So there's a lot of problems with that. But a little bit about them first. They usually perform a very defined, simple function. So they either measure the temperature or measure the pressure. A lot of them sort of simulate voltage regulators and things of that sort. And there's usually hundreds or thousands implemented within a nuclear power plant. And it's the emergent behavior of all these smart devices combined that leads to sort of the successful operation in combination to the main safety systems as well. The thing is, each device has a different safety integrity level. Most that we look at are like SIL 1, but some of them are SIL 4 or SIL 3. And we have found that in the past, I can't give you exact examples, that implementation bugs can propagate from these little smart devices to system-level behavior and cause everything to go wrong. So the bad news is that they're usually written in C and assembly. I get the question a lot is, well, why don't you use Rust? That seems like the obvious answer here. There's a lot of really good reasons why we don't use Rust, and I'll talk a little bit about that in the next few bullet points. But they can also include things like field programmable gate arrays. If you don't know what that is, really don't worry about it. They usually have no underlying operating system. They're interrupt-driven through a time-triggered architecture. So usually some sort of software function is triggered every few seconds, and it sort of interacts with the hardware directly. There's use of pointers and function pointers, and there's communication protocols here that you wouldn't see in a normal computer science textbook. The use of compilers vary depending on the processor and the hardware. Coming from the formal verification community, we think everything is standardized, right? Like you have GCC, LLVM, and all of these nice languages. I didn't realize that these manufacturers wrote their own compilers. That was crazy to me. And some of them wrote their own C language extensions. A lot of them create their own chips, and then everything depends on that architecture that no one else has ever looked at. Sometimes they don't allow us to look at it because it's IP. They say it's IP, you're gonna steal our ideas. Likely not gonna happen, but anyhow, they're not written to be verified. There's usually no requirements or specifications that come with them. They just give you a spec sheet and they go, yeah, that's it. And that's because the nuclear industry is one of their smallest sort of sellers. They don't really care about what the nuclear industry does because these devices are usually implemented in things like farmhouse, manufacturing warehouses, nothing safety critical. So why would they write requirements? Why would they write specification? They usually range between anywhere 10,000 lines to more commonly millions lines of code. So whatever reason you have for not verifying your device, I mean, just remember it could be so much worse. It could look a little bit like this. So how does verification for these types of systems work? The idea is to break down the verification task depending on the system we have and its rigor. We use what's called a safety justification triangle. This is an idea that we came up with at Adelard, but it's now actually been incorporated in the official IAEA software guide. The IAEA is the International Agency of Atomic Energy. You've likely heard about them a lot in the news. They're involved in a lot of nuclear peace agreements. They sort of go dismantle nuclear plants and things of that sort. So we're interested in splitting the verification of properties into 3 different categories. That's property-based approach, vulnerability assessment, and standards compliance. And the number of categories you need to apply depends on the rigor of your system. So for property-based approach, you're looking at things like your system functionality, its actual requirements, things like accuracy, timing, failure integrity, and non-interference. For vulnerability assessment, you're looking at more common errors like data races, deadlock freedom, stack and buffer overflow, and memory safety. For standards compliance, you're looking at things like coding standards and complexity metrics. So 61508, for example, sometimes has a very specific way they want you to sort of implement your system. In the interest of time, I'm going to skip over standards compliance because this is usually depends on the industry. It's also not very much what I'd consider formal verification, but more like linter or things that even your own IDE and compilers can catch. So I'll start sort of with the least rigorous of the remaining two, and that's vulnerability assessment. Vulnerability assessment is defined as defects that manifest themselves only at runtime, causing undefined behaviors, errors, and security vulnerabilities. They're independent of your behavioral requirements or specification, but can affect the functionality of your system, right? If your sort of system ends up crashing at runtime, that obviously affects your functionality. And you're considering things like data races, invalid accesses, memory errors, compiler-defined behaviors like overflow. A few more examples is reading past the end of an array, reading an uninitialized memory location. This is also classed as a security bug, as we've seen with Heartbleed before. Dividing by 0 is something that has plagued many safety-critical systems before. It's a really simple error that you can find, but many people forget to check it. So these bugs are universally present for each language. Each language has a sort of cons. C, notorious for it, C++, and Java have their own issue. Luckily, people have already written specifications for these types of problems and created tools that automatically handle them. So you don't have to. So the tool usually looks a little bit like this. You just give us some code that's sort of compatible with the tool, and the tool sort of has its own technique and internal specifications. Sometimes these tools are public, sometimes they're not, so you might not know what they're doing. And you just get back a list of results. It's pretty simple, actually. It looks a little bit like this. Here you sort of load your project in, and kind of like a compiler, it points to you where you have errors in your code. And sort of on the right-hand side here, you kind of get the list of errors that you would usually see. So things like unreachable code, division by 0, non-initialized variables, out-of-bounds array index. And each tool has its own way of categorizing these errors. They don't do it in a very formal way. Like they call this data flow. Other tools might call it something else. So each tool really has its own language as well. But the good thing about these tools is that they can be flexibly integrated into your development process, but you just need to read the manual to sort of understand how to do everything. And the best thing I think about these tools is that you don't need expertise in formal verification to be able to run them. So what are a few of these tools? Well, the standard tools that everyone uses are usually MATLAB Polyspace and CodeSonar that comes out of Grammatech, which is a sort of a formal verification company. Those two tools I think are used by every system that I have ever come across, especially in aviation as well. They cost a bit of money, but I definitely think that they're worth it, and they're definitely the least expensive of many options that are out there. You also have Facebook Infer, which is sort of a newcomer from the tech industry. Facebook Infer is a little bit different. They also support things like Objective-C, but you don't just run the analysis on your source code. It has to be integrated into your compilation process. So if your compiler is not one of the compatible ones that they use, you're sort of out of luck with that. But it's free, so that's good if it works for you. And then I put Astray in here. Astray is incredibly expensive. Just to buy the baseline of the tool costs like 50,000 pounds. And it's a very sort of intense tool and requires a lot of expertise to use it. But I just thought I'd put it out there for those of you who might be interested in it. The good thing about these paid tools also is that they all provide free trials. So if you're interested in trying it out, they usually give you a month to try it out for free. And you might learn something from it. So far, so good, but as the rigor of nuclear components increases, it's necessary to make sure that the system behaves according to its requirements. So now we care about things like functionality, reliability, robustness, security, and these industrial verification tools just lack the property-driven techniques to do it. So this is where the property-based approach comes in. And its purpose is to analyze functional properties that are provably correct with respect to a mathematical formalization of a program's behavior, right? So it's getting a little bit more math heavy here. It requires defining functional requirements into a formal specification language. And this is a note that I always like to make, because usually a lot of people who try to read formal verification papers might be confused by this term, but there is no such thing as correct behavior. It's really all relative. There's limitations to models, there's limitations to the specifications that you write, there's limitations to how well you can sort of define the environment that your system operates in. And there's no formal verification technique that's perfect, and that's really important to remember. There's always pros and cons. So there is no tool out there that you can just put your code through and say, it's provably correct. So we can't really use industry tools here, so we must look at academic tools, because that's where a lot of the state of the art happens. But academic tools have a lot of assumptions and are definitely a bit more complex. So some of the assumptions that I struggle with is that there's an assumption that you have a standard C compiler, for example. You're using GCC or LLVM. It's the same with Java. There's always an assumption that you're using something that's standard out there. There's an assumption that you have a standard architecture, like Intel x86 or ARM. I mean, my whole career in this field, I've only ever seen an ARM chip once. The rest of them have been sort of custom made by the manufacturer. There's an assumption of an underlying operating system, that you have a scheduler and memory management. These are all things I took for granted when I was in academia, because I no longer see them. And there's little to no support for embedded devices or interrupt-driven systems. There's a lot of papers that say they do support them, and then I read them, and they don't really. And this is something that probably affects everyone in this room, that they're not scalable beyond 10,000 lines of code. That's the reality of the tools. So getting into the formal techniques of these tools is a bit out of scope for this talk. I mean, you can do a whole PhD on it, but instead I just have 10 minutes left. So instead I'll focus on writing specifications for tools that might already exist out there in case you're interested in using them. So I keep saying specifications. Specifications are actually different from requirements, and some people use them interchangeably, but I sort of want to make a note on what they mean. It's a statement expressed in a language whose vocabulary, syntax, and semantics are formally defined. They're usually based in mathematics and not natural languages like most requirements are. And specifications expressed in it vary on the language that you have. They can be high level, low level, both. They're usually some subset of math domain, so it depends on that as well. And since the formal specifications are mathematical, the whole point is that they can be analyzed using formal methods. So this all might sound a bit scary, but actually writing specification comes in many different flavors. So I want to go through a few to sort of introduce you to them. So this is what I call an annotated specifications. They're specifications that you can implement while you're sort of writing your code. This is what I would consider more of a lower level specification. This is ACSL, which stands for ANSI specification language. And in this case, you have some asserts. You have an assert true at the top, and then you have some sort of while loop. And once you exit that while loop, you want to make sure that x is equals to 0. So what this really is saying is the value of x will always be 0 after execution of the loop code. You can definitely improve on this. For example, before you go to the loop, you don't want to have a negative number. You can add an assertion at the top to sort of make that specification a bit stronger than this, because this is quite a weak specification, actually. Your compiler will obviously ignore this because this is just a comment, and then what you would usually do is take a model checker or an abstract interpretation tool and then check this specification against the code. We use Pharmacy to do this. Pharmacy supports these annotated specifications. There's more standalone specifications, which is what I did my PhD on, actually. And in this case, temporal logic is an example of that. There are specifications written separately of the program, and temporal logic can express high and low level system properties. So you have something like AG, y is greater than 0. This is more of a lower level specification. You're talking about a specific variable in the program that you have. So you're saying for all states on all execution, y is always greater than 0. You can also define more higher level specifications in temporal logic. In this case, GF task enable implies GF task execute. What this is saying is if a task is enabled infinitely often, then a task will be executed infinitely often, aka resource starvation, right? People who work in distributed systems are familiar with this. If you have a task that requests a resource, you must eventually give it that resource. And finally, there's design specifications, which is a bit separate from the last two, because these specifications don't reason about your code, but instead they sort of provide an intermediate design language for you to reason about your entire requirement system. So TLA Plus is really known for this, and up here I only wrote the TLA Plus specification. I didn't write an example of what a design would look like. But the idea is, instead of going directly to implement your code, it turns out a lot of bugs don't come from code, but from your actual design. A lot of times the requirements that you have are inconsistent or incompatible, and the design itself might be incorrect. So the idea is to write this out in TLA Plus first before you get to the implementation stage to sort of get rid of bugs in your design and your requirements. So here, the example of specification for TLA plus says, given a set of numbers, return the numbers in that set that are the sum of the two other numbers in it. Right, so it's a bit heavy on the math side, but TLA plus actually has a huge amount of resources, and I think it's really easy to learn. There's a huge amount of amazing books out there for it. And like I said, after that, you would write some sort of high-level design using a similar language and then sort of model check them against each other. So what tools can help us with verifying these specifications? So I put up some if you're interested in them. Pharmacy is one that's used the most in aviation and nuclear. This is the one that I've been using a lot of. And we use ACSL, and it supports also some other specification languages for it. The technique for it is abstract interpretation. There's many other famous tools like CBMC and USMV, TLA+, and many other academic tools out there that exist. But all these tools, with the exception of ASHRAE, that's actually a really powerful tool, have the limitations I've discussed about earlier academic tools. So what we actually do in the nuclear industry is focus on a subset of safety critical systems to verify, and verify them and their non-interference from other functions. So this is sort of our workaround to the lack of scalability, but it works in a lot of cases. So in the absence of good tools, you might be wondering, well, I don't really see a point in writing specifications. This sounds like it's gonna take like way too much time. Why should I do this? Well, I would argue, even if you don't have any tools, you should write specifications anyhow. I think the development of specifications provides really unique insights to the software requirements and software design. You're gonna find that your requirements are not as good as you think they are. They're incomplete, they're weak, there's some fundamental flaws in your design. I've run into many cases where there's requirements are sort of at odds with each other. So I think actually this is always a good exercise for everyone to do. And then if you go ahead and write formal specification, then you might as well try out some of the few tools that exist out there. So let's say you went ahead and ran all of the tools possible and even wrote some specifications. That's all grand. Now what? This is actually what I spend most of my time doing. No matter what amazing automated tools exist out there or will exist in the future, manual inspection and judgment is required at the end of the day. That's sort of the bottom line. There's no formal verification or static analysis tool that's gonna find all your bugs and fix them for you. There's some really important questions that you have to ask. Are the bugs false positives? The tools actually produce a huge amount of false positives depending on if it can understand sort of your compiler or your language. Are they relevant to the safety and security of the system? Which class of bugs are more critical than others? Let's say that all the bugs that you have are valid and you found 200 bugs and you have sort of a short time span to fix them. Which one do you sort of say, oh, this one's more important than others? That's actually really hard to classify bugs. What is the probability of the actual bug occurring? What is an acceptable level of failure? Everyone here is an SRE. They know that failures will eventually happen. No system is failure-free. But what is an acceptable level of it? And can testing and field data demonstrate infeasibility of a bug? So this is an example I always like to give, which is we were looking at a device recently, and we ran some analysis tool on it, and we found 6,000 data races. You would think that's it, you know. There's a problem with this device. It's not going to be installed. That's the end of it. Well, a lot of field studies for this device showed that in the past 30 years, none of these data races ever occurred, right? Is there a problem with the reports? Is there a problem with their logging? Is it the case that these bugs are false positives, or is it the case that their likelihood of them happening is very, very low, even though they're valid? And what efforts are required to repair a system? Do the repair themselves pose a safety and security threat, and what is the impact? There's been many cases where you think that you found a bug and you think, okay, I'll just fix it, that's it, and then I'll redeploy the system, and then you find hundreds of other bugs afterwards that come up, and your whole system can collapse just from this one bug. And that's no different in these sort of components. We have to really think carefully, you know, if there's a bug, if it's worth fixing, right? And then if it's worth fixing, what's the probability of it? What's the probability that that's not gonna break other stuff that's working well? And finally, specification correctness, sort of Nancy emphasized this a lot in her talk. Getting it right is very difficult. You know, there's a lot of human error in the process, and even if you use things like SCPA and STAMP to think about your requirements as a whole, you might not catch every sort of interaction that you need to consider. Now you might be thinking, well, these questions aren't relevant to me. I don't work on safety critical systems. But the whole point of IEC 61508 and these other standards that exist is to promote system dependability. They're not there just to be difficult for the manufacturer or the regulator. And the core principles of IEC 61508 is about system dependability, which consists of attributes, threats, and means. I'm only going to talk a little bit about attributes. So we care a lot about availability, the readiness for correct service, reliability, continuity of correct service, safety, absence of catastrophic events, integrity, absence of improper system alteration, and maintainability, the ability for a process to undergo modifications and repairs. And this is super important for us. And like many people in the SRE community, we care a lot about traceability and logging, because without that, we wouldn't be able to modify a system and maintain it. So before you head back tonight, I wanted to leave you with some thoughts. There's many standards that exist out there, and their whole purpose is to increase system security and reliability. Applying the best practices, sort of adopted from those industries, I think is always a good idea. Formal methods should be one of the many tools you have in your toolbox. There's so many studies that show that it promotes system dependability. We don't just do it for fun. So you should really consider it and try out some of these tools, especially because they're free. Take advantage of them. Tell your devs, do you use C, C++, and Java? If you use Python, unfortunately, there aren't many formal verification tools for it. But the investment cost can be lower and more rewarding than you anticipated. And I also want you to consider regulatory frameworks for safety critical systems as the scope of future technologies and frameworks that you develop. More and more, every day, systems increasingly interact and are becoming safety critical. There are so many cases I've seen, especially with medical devices, that part of their functionality relies on the cloud, right? And so there's sort of an outage, death could happen. Every day, tech infrastructure is becoming more complex and it's becoming more safety critical. So sort of this regulatory frameworks aren't sort of too out of scopes. All right, and that's it. And if you have any questions, please don't hesitate to ask. This is my Twitter handle in case you'd like to reach out and talk a little bit more at a later time. Thank you.